The exploration of our home solar system is far from complete. What spectacles once took place on Mars? What secrets lie dormant beneath the surfaces of Saturn's and Jupiter's moons? These and many other questions remain to be answered in future research missions. Nevertheless, it's no less essential for experts to understand the phenomena and constellations outside our solar system. Especially the search for new, possibly habitable exoplanets has an incomparable importance within modern space research, and which celestial bodies would be better suited for the exploration of alien worlds than those objects that are practically right on our galactic doorstep because of its proximity to the solar system. The binary star system, Alpha Centauri, has repeatedly become the focus of scientific interest. Now we'll show you what we've learned so far about this cosmic system, and which highly complex space telescope will help us decipher the regions around Alpha Centauri in the future. Want to learn more about the groundbreaking discoveries and unique phenomena in space on a regular basis? Then remember to subscribe to our channel and click on the bell to join us on our journey to the greatest mysteries of the universe by giving us a thumbs up. You'll be showing us that we can keep you engaged with the content of our posts. Alpha Centauri, just 34 light-years away from our home solar system, more precisely in the constellation of the Centaur in the southern sky, is Alpha Centauri. As already mentioned at the beginning, this designation not only denotes a mighty celestial body, but a double star system. This system consists in detail of the brighter yellow star Alpha Centauri A and its orange counterpart Alpha Centauri B, together with the red dwarf Proxima Centauri, which is the closest star to the Sun at a distance of about 25 light-years. Alpha Centauri forms a so-called hierarchical triple system. If you want to examine the double star with the naked eye, you will not be able to see that it consists of two different components as a telescopic object. The true composition of Alpha Centauri can only be revealed with the help of a telescope as a star of the first magnitude class. The double system is the third brightest object in the firmament, whereas Alpha Centauri A is the fourth brightest star in the night sky. To orbit each other once on their strongly elliptical orbits, the gleaming celestial bodies need 79 years. The distance between Alpha Centauri A and B varies between 11.5 and 36.3 astronomical units. Remember, the length measure of the astronomical unit, or AU for short, corresponds approximately to the average distance between our blue home planet and the Sun. Rounded up, 1 AU measures to about 9 million miles during detailed investigations of the orbital period, and the semi-axis experts succeeded in determining the total mass of the double star system, which clocks in at 2.08 solar masses. It's generally assumed that both components of the double constellation were formed about 6.5 billion years ago. Concerning their characteristics, the stars are classified in the main sequence. This means those stars that release radiation energy from hydrogen burning in a core. Although the two celestial bodies were formed at about the same time, it's foreseeable that Alpha Centauri A will evolve to a red giant much earlier than its steady companion due to its larger intrinsic mass. Both stars in detail. Just like our Sun, Alpha Centauri A is a yellow dwarf of the spectral type G25, since the celestial body also has some other similarities with our host star. It's often referred to as the closest solar twin to Earth. For example, Alpha Centauri A has a diameter equal to 1.22 times the diameter of the Sun. The mass of the star is given at 1.1 solar masses. At the same time, it emits about 1.52 times more radiation than our native parent star Alpha Centauri A, and the Sun are also very similar with respect to the prevailing surface temperatures. While the thermometer on our central star averages 9939 degrees Fahrenheit, the average temperature on the object 34 light-years away is 9981 degrees Fahrenheit. A closer look at the chemical compositions of the two celestial bodies shows that they differ strongly with respect to the proportion of heavy elements. Alpha Centauri's heavy element content of 274 is 70% higher than that of the Sun. The remaining components of the star are composed of 71.5% hydrogen and 25.8% helium, with an intrinsic diameter of 750,000 miles. Alpha Centauri B is significantly smaller than its cosmic counterpart. While Alpha Centauri A ranks fourth in the list of the brightest objects in the night sky, Alpha Centauri B is only 21st in this category, with an average surface temperature of 9,081 degrees Fahrenheit. The star of spectral type K1 is only slightly cooler than the Sun, but due to its smaller surface, it achieves only 50% of the radiant power of our host star. In the course of their investigations, the researchers realize that Alpha Centauri B needs 41 days to rotate. Once around its own axis, to put this into perspective, it takes about 25 days for the Sun to complete a full rotation, Proxima Centauri. As we mentioned at the beginning, the binary star system Alpha Centauri forms a superior triple system together with Proxima Centauri. Although the actual affiliation of Proxima Centauri to this cosmic group has been much discussed in the past, its galactic membership is now taken for granted. The star closest to the Sun is separated by a distance of about 12,900 astronomical units, which corresponds to 1,000 times the distance prevailing between Alpha Centauri A and B. Despite this huge spatial gap, a detailed scientific investigation showed that the red dwarf is indeed gravitationally bound to the pair of stars. However, before Proxima Centauri orbits its counterparts, a tremendous amount of time elapses. The orbital period is about 600,000 years. Because of these circumstances, the object in the southern sky is sometimes called Alpha Centauri CC, the search for planets. For about 5 years, we've known that Proxima Centauri serves as host star for at least one exoplanet with a minimum mass of 17 Earth masses at the same time. Evidence has already been discovered, suggesting that another companion with just 1/3 of the Earth's mass is orbiting there, in the case of Alpha Centauri A and B. However, evidence of the existence of exoplanets. There has so far been lacking. The computer models of the experts show, however, that terrestrial planets could very well form in the realms of the double star system. At present, there is one hypothetical celestial body that repeatedly makes astronomical headlines: Alpha Centauri AB. It could be an exoplanet which orbits the star component A in a distance of 1.1 AU, meaning the celestial body would be within the habitable zone of its system, also worth recalling. The habitable zone means that distance range in which a planet must be to its host star, so that the basic condition for the development of life can be present there: the existence of water in permanently liquid form. However, since so far, researchers have not excluded the possibility that Alpha Centauri AB is in truth another astronomical structure. The theoretical exoplanet has only candidate status, while the existence of rocky planets in the realms of Alpha Centauri is not improbable. The presence of gas giants like Saturn or Jupiter can be generally excluded. This is because, according to our knowledge, gas planets cannot form in binary star systems due to gravitational perturbations in order to finally be able to report the first galactic bullseye in Alpha Centauri. In the foreseeable future, experts are currently placing great hopes in the development of a piece of equipment that should revolutionize the exploration of the corresponding star system, the Ptolemy telescope. The Ptolemy mission, this ambitious but relatively inexpensive project, is to be put into action as soon as the year 2023 and to supply important new discoveries about those strange worlds that might be orbiting around Alpha Centauri in detail. The optics of the Ptolemy Space Telescope, which was created as part of a collaboration between NASA, the University of Sydney, the company Sabre Astronautics, and the Breakthrough Initiatives program, were designed for just this purpose: the search for potentially habitable planets in the realms of our neighboring stars. What distinguishes the Ptolemy telescope from other space telescopes is the fact that the exoplanets in question are to be detected not by means of the transit method, but by their gravitational effect. The gravitational pull of exoplanets always causes minimal irregularities in the motion and rotation of their host stars. These tiny irregularities in turn can show up in the light spectrum through spectral shifts to ensure that the revealing patterns can be detected in detail. The Ptolemy Space Telescope will be equipped with a so-called diffractive lens. This has a very fine corrugated structure which amplifies and refracts the incident light in a special way. The resulting optics are ultimately particularly well suited for identifying discrepancies in the motions of stars in addition to the Ptolemy mission. The Breakthrough Initiative is already making plans to analyze Alpha Centauri in more detail. Accordingly, the goals of the research program, which is looking at ways to contact intelligent extraterrestrial life, include the deployment of mini-probes. The unmanned spacecraft are to be brought to the double star system with the help of light sails and give terrestrial researchers an even more direct insight into the environment of Alpha Centauri. Now we want your opinion. What do you think about Alpha Centauri and the future exploration missions? We're already looking forward to your comments. Finally, please have a look at the other exciting videos on our channel, which we have linked for you in the credits. Thanks for your interest. Take care, and we'll see you next time.